We introduced the equilibrium well equations. Now we're going to talk more generally about equilibrium head or the equilibrium hydraulics in groundwater, a groundwater table, or the groundwater head overall. And we're going to do it in 1 and 2 dimensions. And when we're talking about the head, we're going to draw equipotential lines for it. In other words, contour lines. So this is the same thing as topo lines for elevation of the ground. We're going to have topo lines or equipotential lines for the groundwater head. Groundwater flow is an example of potential flow. In this case, water flowing from high head to low head. We see potential flow in other applications also. It's the exact same thing as heat flow, for example. Heat flowing from high temperature to low temperature is the exact same thing as electrical current flowing from high voltage to low voltage. We can use the same equations for each, just the little definitions and the applications are a little bit different. They're not perfect analogies between them. For potential flow, for groundwater, we want to draw the equipotential lines, which I just said was the same as the topo lines. So we'll do a little example here. I have an aquifer, two-dimensional aquifer, and I have the heads along two sides there. And we will draw equipotential, same potential lines, and make a smooth transition. And then a little bit we'll develop the equations for that. As you experienced, my drawing is pretty bad, but I'll try to make an attempt of it. So all this means is that we have equipotential, same potential. We connect the 1030 there with the 1030 there. That wasn't too bad. 1040 to 1040 there. 1050 and so on to 1050 there. And I'll do a couple more. 60 to 60. And I suspect if we have more, it'll get kind of the same shape there. Maybe we'll bring another one back in here. So those are the equipotential lines. Equipotential lines, or the heads. And to make a flow net, we want to also make the streamlines. So the streamlines are the way the water flows, and the streamlines are orthogonal to the equipotential lines, or perpendicular. So I can start making some, we can actually put numbers on them, but the numbers don't really mean anything. They're just relative to each other. I mean, we could use them to calculate flow, but that's a whole other thing. So let's draw some streamlines on this. The streamline, draw perpendicular to equipotential lines and put arrows on the streamlines to show the direction of flow. So it's going to go from, it looks like I drew kind of backwards. I went from low head to high head. The stream lines, the groundwater is going to flow from high head to low head. So maybe I'll put one in up on top here that goes, so I want to go perpendicular. I'll do these in blue, but to this line, and then perpendicular to that line, perpendicular to that line, that line, that line. That one's not too perpendicular, is it? So it's shooting perpendicular, shoots to the next one, shoots to the next one, shoots to the next one, shoots to the next one. So my streamline would look something like that. Whoops, a little wiggly. And so it's going in that direction there. And then I can pick off another one there, and also, again, perpendicular to each of those. The streamlines are perpendicular to the equipotential lines, and look like that. And maybe another one here. That one I'm missing pretty bad. And maybe another one here. Perpendicular, 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 perpendicular. That one's pretty bad too. But that's a flow net. So the flow net, we have the head contours or equipotential lines, and then we have the streamlines showing which direction the water flows. And I'll put a couple more arrows on those. Let's develop some equations for the groundwater contours. Because my writing is so messy, I went ahead and filled in a lot of stuff in here. So I'll just talk through it, and then at the end of this first little section here, we'll do one example that I'll fill in. So Darcy's law is three-dimensional. So if we have a flow going off in some direction, we can resolve that into the x, y, and z components. Little q is the specific discharge, so we can have that in each of the different directions we have. We'll do X, Y, and Z. We could also have an R in there. For each of those, the Darcy's law says that the specific discharge in X direction is equal to K in the X direction, so we can have different hydraulic conductivities in different directions, times the partial derivative in the X direction, or in other words, the change in the X direction. So that's all partial derivative means is the change of head in the X direction, change of head in the Y direction, change of head in the Z direction. So if I walk on the groundwater table and I'm going in X direction, partial H, partial X will be my slope as I go in the X direction. If I'm walking in the Y direction, partial H, partial Y will be my slope as I go in the Y direction. If we substitute these Darcy's law equations into the continuity equation for equilibrium incompressible flow, and again, I'm going to resist my temptation to do fluids here. All that means continuity equation says for a little box of water here, a box of aquifer in our case, in has to equal out. If it's compressible, you can squeeze more in than comes out, but incompressible, in has to equal out. We can have more going in the face on the left here than goes on the face on the right, but it's got to come out some other face. So that's why we have those. Each of these does not have to be zero, but they have to be zero altogether. If I substitute QX here, if I could substitute that into here and then into there, this is what I get. The change in the KX times the change in change in X, and then the Y and the Z direction. Those all equal zero. Now, if we assume that, first of all, the hydraulic conductivity is constant for my little tiny box, it can change a lot over space, but we're developing it for a little tiny box. And then it's isotropic, which means the same in every direction. It doesn't have to be. And I mean, if that's not true, we can do something else, but the math isn't quite as neat. So for our example, we'll do that. So if we do that, we can pull this K, Kx, Ky, Kz all just equals the same K, and we can pull it out of the derivative. So we get K over outside of the derivative there, and then we can pull it over the right-hand side, right? And then this term goes to zero here. So we can eliminate K, in other words. So we just have that in parentheses. And the change of H in X becomes the second derivative. Partial X is on the bottom, goes partial X squared on the bottom, partial squared H on top. So that says the three second derivatives in the X, Y, Z directions added to each other equals zero. Not each of them doesn't have to equal zero, but together they add up to zero. In one dimension, so let's just do the X dimension, then we get rid of those two, and then we get partial squared H partial X squared equals zero. So that would be the one-dimensional Laplace equation. So the second derivative equal to zero is the Laplace equation, or the second derivative in space. In our case, x, y, z, r equal to zero is the Laplace equation. And this is, the zero tells you, by the way, that zero tells you it's equilibrium. We go to the transient case, that term on the right side will not be zero anymore. Now we solve it. Okay. How do we solve? Go back to differential equations, whatever. Okay, so I might write this. I'm do this very simple kind of shortcut. Second derivative of h equals zero. That's what it says. If I integrate that, it's going to go to, I'm just showing arrows, say what it comes out to. We integrate h double prime, or second derivative, we get the first derivative equals 0 times x, or 0, plus a constant. And if I integrate that again, that goes to the first derivative just becomes h equals c1 times x. The 0 is gone, it's just a 0. c1 times x plus another constant, c2. I'll rewrite that here. H equals c1x plus c2. So I have two constants. I need two boundary conditions. We're going to use h equals h0 at x equals 0 and h equals h sub l at x equals l. At x equals 0, we have h equals h0 equals c1 times x, which is 0, plus c2. So h equals h0. Okay, so this just says that c2, so this term cancels out, right? C2 equals H0. H equals H sub L, or the head at distance L, equals C1 times L plus C2, which we know now is H0. This goes to C1, rearrange that, equals HL minus H0 over L. So substituting back up in here, we get that H equals H0 plus HL minus H0 over L times X. So this is the intercept, and this is the slope, which is just the change in head over distance. So it's a straight line. Well, I could have probably told you that without doing all that math, but I just showed that that's a solution to the Laplace equation. Actually, we already said well, get too far into it, but we already said for an unconfined aquifer, the area of flow changes, so you actually have some curvature to it. But this just says that the head is under one-dimensional conditions. It's not true under two or three-dimensional conditions. Under one-dimensional, this is a straight line. So we'll do an example of that. So a specific site, we know that the groundwater head is 910 meters at well A and flows toward well B 200 meters away. So we have, this is at A, it's at 910, and at B, it's at 900. Slope for the water table looks like that. What is the head 40 meters from well A on the line toward B, which would be 160 meters from B, 40 meters from A? So right in here, this is 40 meters and 160 there. What is this head? Well, I'll just use my equation. So our equation is going to be the slope would be 910 minus 900, or really I should write 900 minus 910, right? It's going to be negative slope over 200 equals minus 0.05 feet per feet. So our equation says that H equals H0, which is 910, plus the slope, so in this case, minus 0.05 times the x of 40, 908 meters. What is the hydraulic gradient? The hydraulic gradient is just what we calculate here. It's the slope of the groundwater table, or the slope of the potential. It's minus 0.05 feet per feet. That's the hydraulic gradient, or we might call that dH dx. So we only have x, we could use d instead of a partial. So you've done some groundwater model. We're now going to go into a little more of the Laplace equation, and then we're going to use that to go into a finite difference version of that, and we'll do some more kind of groundwater modeling. What's the fundamentals of the groundwater modeling?